Hi everyone, welcome back to MATA35. Today we're going to be learning about critical points, maximums, and minimums of multivariable functions. So let's go ahead and get started. Let's start by talking about giving a brief reminder of local extrema of single variable functions. So these are things that you covered in your first calculus class. So if you have a function from R to R, so this is an ordinary function, f of x is equal to some y, which is a real number, and we have if something is a local or a relative minimum or maximum, that means that around some small neighborhood around that local minimum, say let's call it x naught, you have that everything is bigger than it, or everything is smaller than it. So this is easier if I draw a picture. Let's draw a picture. So we have some x-axis, we have some y-axis, and we're going to be plotting y is equal to f of x. And so let me just draw something. So maybe it looks something like this. So now we have several different local maximums. So this here, and that there, those are all local maximums because in a small neighborhood around it, so if you were to draw a tiny neighborhood around each of these points, so let's say a tiny neighborhood around this point, everything is smaller. Or if you draw a tiny neighborhood around this point, everything is smaller. Okay, so everything goes down in the tiny neighborhood around it, and so it's a local maximum. We also have local minimums, so that would be this point here and that point there. Oh, and I guess that point there is also local minimum. So these are all local minimums. Because if you draw a tiny interval around it, the function is always smaller, or sorry, always bigger than that point, and so it's a local minimum. So this should be a reminder of stuff you learned in your Calculus 1 classes. It's just basically a local minimum means that, well, everything around it is bigger. A local maximum means everything around it is smaller. But so now, how do we find these local minima? And the way we do this is we use something called critical points. So if you have a differentiable function, one of the things you can do is you can take the derivative of your function, and if it's equal to 0, then that's what's called a critical point. So for example, if we had a simple function f of x is equal to x squared minus 2x, well, let's draw this function. So this function looks a bit like it's a parabola. And so one of the things, this parabola looks, oh, I shouldn't use that color. Let me redraw that in a different color. So it's a parabola. It would help if I could actually draw, but it's roughly speaking this parabola. Okay? So we have this function, and you can see where the local minimum is. It's at this point down, this blue point here. And you can also see that this is a critical point, because if you take f prime of x, that's equal to 2x minus 2. If you set that equal to 0, or if you want to conclude that 2x naught minus 2 is equal to 0, because you're setting it equal to 0, that implies that x naught is equal to 1 is where your local minimum is. And you can sort of see this because what you're saying is that f prime of 1 is equal to 0, which means that the tangent lying there has slope 0, so it's a horizontal line. Okay? Now, of course, just because it's a critical point doesn't mean that it's an extremum. So it doesn't mean that it's a maximum or minimum. You might have other examples. There's the classic one in one dimension is f of x is equal to x cubed. Well, if you have that, then if you draw out the function, what you're going to see is something like that. And it turns out that if you look for critical points, you're going to say f prime of x is equal to 3x squared, and you're going to set that equal to 0. So 3x naught squared is equal to 0, so x naught has to be equal to 0. And you'll notice that f prime of 0 is actually 0. So if you look at the tangent line here, it is still horizontal, but it's not a local minimum or a local maximum. Instead, it's an inflection point, or sometimes you call them saddle points. So regardless, it is still a critical point, but it isn't a maximum or minimum. In order to figure this out, of course, we had something called the second derivative test, which I'm sure you all learned about, which is if you have a twice differentiable function, so if you take the derivative twice of it, then for any x in R where f prime of x is equal to 0 and f double prime of x is greater than 0, x is a local minimum. And if f double prime of x is less than 0, then x is a local maximum. Now, we don't have enough information if f prime of x is equal to 0 and f double prime of x is equal to 0, but this test allows us to very often answer the question of whether something is a local minimum or a local maximum. So for example, if we go back to our example a moment ago, what was it? F of x is equal to x squared minus 2x. Well, if you draw this parabola out, let me just copy it again. Maybe I'll draw a better parabola this time. Yeah, that one's slightly better, slightly. So what you'll notice is that if you take the first derivative, we did that already, so the first derivative, f prime of x is equal to 2x minus 2, and set that equal to 0, x is equal to 1 is the critical point, where x is equal to 1, but then f double prime of x is equal to 2, and therefore f double prime of 1, since that's the critical point, is also equal to 2, which implies that 1 is a local minimum. Okay, so do we have any questions on that? Let's just make sure everyone's on the same page. I'm going to ask you guys to try it out. So, given this particular function, I want you to tell me if it's a local minimum, a local maximum, or neither. So, f of x is equal to minus x minus 1 squared. And now the key here is, of course, to use the first derivative to find the critical point, and then to use the second derivative to determine whether or not it's a local maximum or a local minimum, or if you don't know. Actually, I should have had don't know there instead of neither, since using the derivative test, you can't actually figure out that it's neither of those, because sometimes you'll have a local minimum where the second derivative is also equal to 0. One easy example is f of x is equal to x to the 4th. But anyway, so let's see. The key here is just to take both derivatives. I'll give you all a moment to work through this. Okay, so we're getting a lot of A's in chat. Well, let's take a quick look and see what happens. So f of x is equal to minus x minus 1 squared. Let's see, we got a few B's. Oh, there is no C in option. Yeah, I did A, B, E in this particular case, but you can largely ignore that. So f of x is equal to minus x minus 1 squared. So f prime of x, by the chain rule, is equal to minus 2 times x minus 1. So therefore, we have a critical point. The critical point is at minus 2 times x naught minus 1 is equal to 0, which implies that x naught is equal to 1 is the critical point. Now, what else do we have? We also know that f double prime of x is then equal to minus 2, which means that f double prime of 1 is equal to minus 2. But if it's minus 2, then that means that this has to be a local maximum. So thus, x naught is equal to 1 is a local maximum, not a minimum. So it's actually B here, not A. Yeah, so you have to be careful. When the second derivative is positive, that means it's a local minimum. When it's negative, that means it's a local maximum. You can think of it as plus then minus. If it's 0, no, so if it's 0, it might be an inflection point, it might not. So that's a little bit more complicated, and you have to do further tests. In this particular case, you can graph it out, and that will also give you the answer. So this thing looks like that when you graph it out. But yeah, so when it's 0, the second derivative test just doesn't work, and you have to use other tests. Okay, so it looks like some of y'all remembered that, but basically this is the second derivative test from single variable calculus. Now, of course, we're going to have to generalize it, because this is calculus 2, so we're going to be generalizing it to multivariable calculus. So, what does it mean for something to be a local minimum or maximum of a multivariable function, so f of xy going to some value? Well, remember that when we have f of xy, what we basically want is we have a plane, and then we have a surface on top of that plane, because for every xy coordinate, you have some z value, right? So this looks something like this. This is f of xy is equal to x squared plus y squared, which looks sort of like a parabola, except it's in 3D. And now the question is, does this have a local minimum? What does that mean? Well, a local minimum just means that everywhere around it, so if you draw a small rectangular box around it, everywhere around that point is bigger than it. So in this case, we do actually have a local minimum, and that's at this point here. So local minimum at the origin. Okay, and of course you can have something similar, so you can have local maximums as well. So I drew, I plotted a much more complicated figure. So this is a sort of fun figure to plot, and computing the derivatives is actually super hard for this, and so the function is not well defined at the 0 point, but let's take the limit as the function goes to the 0 point. Ignore all that, and just look at the picture. And here we have a local maximum at the origin. So local max at 0, 0, roughly speaking. Really, I should say that we also have f of 0, 0 is equal to 0. Because otherwise, this function's not well defined at 0. Okay, so any questions about that? Basically, it's the same idea. A local minimum is just the place where everything around it is bigger. A local maximum is just the place where everything around it is smaller. Now, in order to find these things, well, you might think, well, in one dimension, we used these derivative tests, right? So we're able to use derivative tests, and those told us, A, where the critical points were, and B, it also told us, using the second derivative test, it told us whether it was a minimum or maximum, or if we can't figure it out from the data at hand. So now, we need to remember what derivatives are in higher dimensions, right? So remember, when we have derivatives in higher dimensions, there are a couple of different important facts about them. So the first thing is we had an entire tangent plane. So for every single point, so if we pick a point here, we had an entire tangent plane to the surface at that point. And f sub x, or partial f partial x, says how fast f grows in the x direction. So this here, let me put this in orange. This here in the x direction, that's this line here. Okay? And we also had partial y, which is how fast it grows in the y direction. So in this particular case, that's this line here in blue. So our partial derivatives say in two particular directions on the plane, how fast does a line on the tangent plane grow? Okay, so as you start from that point, if you're walking in a particular direction, how fast does the function f grow? Okay, so this was the whole point about partial derivatives that we covered in the last lecture. And one of the other important facts, which we mentioned, but we're not making too much use of, is that you can encode all this information into something called this gradient vector, which has both of the partial derivatives, and it tells you, by multiplying it against the particular vector, how fast the gradient grows in any particular direction. So now, if you wanted to go in some other direction, let's say you wanted to go in this direction, this green direction, well, you just need to multiply that direction vector by the gradient matrix, the gradient vector, and that'll tell you how fast it grows in any other direction. So that's the basic premise behind these sorts of gradient vectors. It tells you how quickly your function grows in any particular direction as you go in sorry, let me say this is u. So as you go in this u direction, how fast does the function grow? Okay, but now we have this idea of a tangent plane, right? And so it's the plane that's spanned by f sub x and f sub y. Because if you have any two intersecting lines in a three-dimensional space, then they define a plane. Well, unless they're entirely collinear. But ignoring that, if you have two different lines, then they define a plane, right? So now, if you think about it, what we were talking about when we were talking about the second derivative test, or sorry, when we were talking about the critical point test, is we wanted a horizontal line. Now, in higher dimensions, what we want is also, if you look at this, I also drew these tangent planes at each of the critical points. And basically what we want here is we want a horizontal plane instead, for the critical point to be the case. For it to be a critical point, you want the tangent plane to be completely horizontal. And it turns out that there's a very easy test for this, which is you test whether or not both of the partial derivatives are equal to 0. Because the partial derivatives say how much it grows in the x direction and how much in the y direction. And so if both of those grow 0, so if both of those are horizontal lines, then the entire plane is also horizontal. Now, just like in the previous case, we have, so we can have a tangent plane and it can correspond to a local minimum, like this one here. So this one here is a local minimum. Or you can have something called a saddle point. So sometimes, even though you have a tangent plane that is completely horizontal, the function isn't a local minimum or local maximum, because in one direction it's a local minimum. So if you look in one direction, so along the green direction here, if you go anywhere along the green direction, you fall down, and so it's a local maximum. But if you go along the red direction, you grow up, and so it's a local minimum. And so this is a saddle point, or one kind of saddle point. So now the key here is that if it's 0, it's an inflection point, right? So if it doesn't have to be is the problem. So that's the thing. So when you talk about inflection points, you normally talk about a changing concavity or concavity. If it's 0, then you don't necessarily know for certain. Does that answer your question? Very often it is. That's one of the other cases you can have. Okay, so now let's move on. So now we have these critical points, and we have some of the critical points are local minimums or local maximums. Some of the other critical points will be inflection points or saddle points or these other things. And we're going to categorize all this other behavior under the term saddle point. And so basically, a saddle point is a critical point which isn't a minimum or maximum. That's how we're going to define it for this class. So the prototypical example looks like a horse riding saddle. So if you look at a horse riding saddle up here, you'll see that this goes up in one direction. So it goes up going in both directions along one axis, and it goes down in both directions along the other axis. So this is why they're called saddle points, because they look sort of like a horse's saddle. And you'll see that those correspond to the green and red lines on the other picture of a saddle point further down. Okay, so this is the basic example of a saddle point and where they get their name from. Other examples might look a little bit different. So there are other examples that are also saddle points. So for example, you have this saddle point here, which is an inflection point, which looks a lot more like y equals x cubed. So this one here. So you have this behavior. So that's another type of saddle point, which also is an inflection. Or you have these weird things where along one direction it looks like y cubed, but along the other direction it looks like a parabola. Okay, so you can have all sorts of weird saddle points, but the basic idea is it's a critical point that isn't a local extremum, and that does include inflection points, but it also includes other weird behavior. Okay, so now that we have this, the question is, we have this equivalent of a higher dimensional first derivative test, right? So we can find the critical points by just setting both of the partial derivatives equal to 0. What about a higher dimensional second derivative test? So for a single variable function, if something is a critical point, we just check if the second derivative is positive or negative, determine if it's a minimum or maximum. Is there an analogous test for a critical point of a multivariable function? And of course the answer is yes, or we wouldn't be having this class. But it's actually non-trivial to decide what the test ought to be. So let's try something. Let's try something first. So this is attempt 1 at getting a second derivative test. And one thing you might think is, well, in the first case we said that something was a saddle minimum or maximum depending on the second derivative. What if we just ask if all these second derivatives, because we have 4 second order partial derivatives, we can just ask if all 4 of them are positive or respectively negative. So let's try it out. So I have several functions here, and oh, come on. Well, let's do the first function first. And I'm going to ask you if it's a minimum, maximum, or saddle point. And what we can do is we can just look at these things. So let me find my okay. So let me reset the chat, and you should go into GeoGebra and ask whether or not something is a minimum, maximum, or saddle point. And let me share my screen. So where is my screen? Sorry, I am having technical difficulties. Okay, so can you guys, hopefully you guys can see my screen now. I currently have highlighted x squared plus xy plus y squared. So what is this? So it looks like, oh, sorry, you can't see my, oh, okay, you can't see the poll when I'm in the screen. But yeah, so it looks like everyone's been answering, a lot of people have been answering A's. So we have a lot of A's because if you go back to this screen, well, yes. So it looks like you have a minimum at the point 0, 0. So that works out, right? And let's double check that the 4 partial derivatives are correct. So here we have f sub x is equal to 2x plus y, and f sub y is equal to x plus 2y. And so that means f sub xx is equal to 2, f sub xy is equal to 1, f sub yx is also equal to 1, and f sub yy is equal to 2. Oh, except you can't see that because I'm in the wrong screen again. Okay, so you can see that if we compute all the different partial derivatives, second order partial derivatives, they are all positive, and this is a minimum. So that would seem to suggest that, at least for this example, things do work. So now I want to ask you all to do it yourself for the case where f of xy is equal to x squared plus 2xy plus y squared. And let's first check to make sure that all the all of the partial derivatives are the correct sign. So let's say we have f of x here is equal to 2x plus 2y. F of y is equal to 2x plus 2y again. F of xx is equal to 2. F of xy is equal to 2. F of yx is equal to 2. And f of yy is equal to 2. And so let's see. So is this a minimum, maximum, or saddle point? Okay. So it looks like we have a lot of C's in chat. And yes, this is correct, because if you go back into a visualizer, and you change this here to 2xy, what you see is that in one direction, it does actually go up and down. But in the other direction, so in one direction it does look like a minimum, but in the other direction it's flat. And so it doesn't actually go up or down, and so this is not something we're going to call a local minimum, and we are going to call this a saddle point. Okay, so let me reset again, and let's do our very last one. Sorry, I have way too many windows open right now. Go back here, and let's do our very last one. Let me reset again. And so for our very last one here, if you compute these out, you'll find that f of xx is equal to 2, f of xy is equal to 4, f of yx is equal to 4, and f of yy is equal to 2. So now the question is this a saddle point? Okay, it looks like sorry, not is it a saddle point. Is the minimum and maximum or a saddle point? Okay, so it looks like we have a lot of votes for saddle point, also because I accidentally told you all the answer there. But if we look at this now, if we go back to Chrome and we change this to 4xy, you'll see this is very much a saddle point. In one direction it goes down, and in the other direction it it goes up along one axis. Okay, so let me, okay, there. You can see it a little bit better now. Okie dokie. So, as you can see, this test doesn't work. It doesn't work because, well, for any number of reasons, but we can see that even though we have all positive second-order partial derivatives, you still can have saddle points. Note that we didn't end up having any maximums, but we did have, sometimes it's a minimum and sometimes it's a saddle point. So this test is not good enough. Well, last time, we mentioned something called the Hessian matrix. So now, we said that this was analogous to the second order partial total derivative. So instead of the partial derivatives, we're combining them all together into a total derivative. And it looks something like this 2x2 matrix with 4 entries, which are all of the partial derivatives all put together. So, but of course, when you have a matrix, it's harder to define what you mean when you say is something positive. Like, what does it mean for a matrix to be positive? Or what does it mean for a matrix to be negative? And now, the answer here depends on whether we're talking about matrix addition or multiplication. So if we're talking about addition, well then a matrix, you can think about it as positive if all the entries are positive, which is what we just checked. But when we're talking about matrices, we're often talking about their action via multiplication on a vector, right? So we talked about how matrices can be thought of as transformations of vectors via matrix multiplication. And so if we're talking about matrix multiplication, it turns out that what it means to be positive is actually slightly different. Now here, we are going to return back to what we were talking about with eigenvectors and eigenvalues. So remember, you can think about what a matrix does to a vector by what it does to each of the eigenvectors if they form an eigenbasis. So in this particular case, this matrix that we studied last on Wednesday. Not on Wednesday. This matrix that we studied last week when we were still in the linear algebra section, what this matrix does is it takes one of your basis vectors and multiplies it by 3, and another one of your basis vectors and multiplies it by 1. And so now, when you're thinking about what eigenpairs do, you can think about that as basically the sort of scaling factor, and you can think about that as a type of multiplication. And this turns out to be the right way of thinking about the generalization of positive and negative to matrix multiplication, is to just look at the signs of the eigenvalues. And so this is what we call the Hessian, what we're calling the Hessian test for whether or not something is a local minimum or maximum. So given a twice differentiable function, we have this Hessian matrix. Now, if you have a critical point of this function, then of course the first derivatives are both equal to 0 at that point. And we also know that it's a local minimum. It's a local minimum if all the eigenvalues are positive. So basically, if you're saying in both of your major directions you have a positive eigenvalue, then it's a local minimum. Similarly, f is a local maximum if all the eigenvalues are negative. You can think of it as showing that everything's curved downward in both directions. And it turns out that we can also even say that some things are saddle points if one eigenvalue is positive and one eigenvalue is negative. Because it goes up in one direction, along one axis, and goes down along a different axis. And so, again, this test doesn't always work. We don't have enough information if any one of the eigenvalues is 0. So if any eigenvalue is 0, then this doesn't work. But as long as both eigenvalues are non-zero, this tells you whether or not it's a local minimum if both of your eigenvalues are positive, it's a local maximum if both of them are negative, and it's a saddle point if one is positive and one is negative. So let's go back and see our previous examples. So this is what we graphed out a moment ago in the visualization software for f of xy is equal to x squared plus xy is equal to plus y squared. Of course, as we said there, f of x is equal to 2, f of xy is equal to f of yx is equal to 1, and f of yy is equal to 2. So this gives us a Hessian matrix, which is equal to 2, 1, 1, 2. So note that you have to be a little bit careful, because what we're really saying is that we have a critical point. Oh, sorry, let me put this in a different color. So what you have to be a little careful, because we had f sub x is equal to 2x plus y, and f of y is equal to x plus 2y, and we're setting these both equal to 0. And it turns out when you set these both equal to 0, what you end up getting is that x is equal to 0 and y is equal to 0. So you have a critical point at the origin, 0, 0. Okay? So the first thing you need to do is you need to find your critical point. And the second thing is, then you need to find that this is, if f of x, x is equal to 2, then f of x, x at 0, 0 is also equal to 2. And f of x, x, y is equal to f at 0, 0 at 0, 0 is equal to 1, and so on. Okay? So here what we're really saying is that h of 0, 0, the Hessian matrix at 0, 0, is 2, 1, 1, 2. And so now all we have to do is we have to find the eigenvalues of this. And so the eigenvalues of this are, of course, 2 minus the determinant of 2 minus lambda, 1, 1, 2 minus lambda is equal to 4 minus 4 lambda plus lambda squared minus 1, and we're setting that equal to 0. So that gives us lambda squared minus 4 lambda plus 3 is equal to 0. Lambda minus 1 times lambda minus 3 is equal to 0. So lambda is equal to 1 or n3. So this gives us two positive eigenvalues, so local minimum. Okay, let's do a couple more. So we had this other example, which here, so in this particular case, we again have the critical point at 0, 0. So in order to find the critical point, you solve for f sub x is equal to 2x plus 2y. So this actually doesn't work out as well, but we can check that. So there is a critical point. So critical point at 0, 0, which is pretty easy to check. We're not going to solve it this time because you actually end up with an entire family of critical points. But we had f of x of xx is equal to 2, f of xy is equal to f of yx is equal to 2, and f of yy is equal to 2. So we have a Hessian matrix at the point 0, 0 is equal to 2, 2, 2, 2. And if you find the eigenvalues of this, 2 minus lambda, 2, 2, 2 minus lambda, this is equal to 4 minus 4 lambda plus lambda squared minus 4 is equal to 0. So lambda squared minus 4 lambda is equal to 0, and lambda times lambda minus 4 is equal to 0, so lambda is equal to 0 or 4. So here, we actually can't say, so cannot say using Hessian test because one eigenvalue is 0. Of course, you can look at the picture and we know that it's a saddle point, but you can't actually use the Hessian text for this example. For the last example, though, we are able to use the Hessian test. So again, the first thing we do is we find the critical points. So f sub x is equal to 2x plus 4y. F sub y is equal to 4x plus 2y. These are both set equal to 0, so that implies x equals 0, y equals 0 is critical point. And so now that you have these critical points, then what you do is you take f sub xx is equal to 2, f sub xy is equal to f sub yx is equal to 4, f sub yy is equal to 2, and therefore your Hessian matrix at 0, 0 is equal to 2, 4, 4, 2. We want to compute the eigenvalues, 2 minus lambda, 4, 4, 2 minus lambda, that's equal to 4 minus 4 lambda plus lambda squared minus 16, which is equal to 0, and you end up getting lambda squared minus 4 lambda minus 12 is equal to 0, lambda minus 6 times lambda plus 2 is equal to 0, lambda is equal to 6 and minus 2. So this here is a saddle point, because one direction positive and other direction is negative. Okay, let me do one more example together, and then I'll have you all try it out. So here, we're going to, so in both of those cases, the Hessian matrix was a constant matrix. Sometimes the Hessian matrix is not constant, as in this weird function I have here, which looks sort of like a cap on like certain types of like paint cans, like so the paint dispenser thingamajigs. But anyway, so we have this function, which is a little bit weirder, and of course the first step is we need to solve for the critical points. So the first thing we do is f sub x is going to be equal to, well, you need to use the chain rule, so this is 2x times cosine of x squared plus y squared plus 1.1 times 2x. F sub y, actually let me rewrite that first into a slightly nicer form. So this is equal to 2x times 1 plus cosine, 1.1 plus cosine of x squared plus y squared. And similarly, f sub y is equal to 2y cosine of x squared plus y squared plus 1.1 times 2y, which is equal to 2y times 1.1 plus cosine of x squared plus y squared. And note that this thing here, so this interior here, that is not equal to 0. And this is because when we look at the graph of cosine, cosine is, of course, always bounded between 0 and 1. And therefore, if I add 1.1, so that's 1, and that's, between negative 1 and 1. And so if I add 1.1 to it, it's always positive. And so therefore, it's never equal to 0. And so when we're solving for this, so we need to solve for the critical points, solve for the system of equations 2x 1.1 plus cosine x squared plus y squared is equal to 0, 2y 1.1 plus cosine x squared plus y squared is equal to 0. Since this stuff inside the brackets is always not equal to 0, you can divide both sides by that. And so this gives you the system 2x is equal to 0 and 2y is equal to 0, which of course implies that x is equal to 0, y equal to 0 at the critical point. So critical point at x naught, y naught equal to 0, 0. Okay, which is this point here, as you can see from the graph. But so now, how do we figure out whether this is a local minimum or maximum? Well, looking at it, you can tell that it's a local maximum, but we need to actually solve for this using the second derivative test, or the Hessian matrix test. And so in order to do this, what you do is you have to take the partial derivatives. So here, let's say I copied again fx and fy, so fxx. So you take the the derivative with respect to x again, you end up getting 2x times the derivative of that entire thing. So that ends up being another 2x times minus sine of x squared plus y squared, plus 2 times 1.1 plus cosine of x squared plus y squared, which ends up being equal to minus 4x squared sine of x squared plus y squared plus 2 times 1.1 plus cosine of x squared plus y squared. Okay, so that's just using the chain rule, so you need to be very comfortable taking partial derivatives. And similarly, so this implies that fxx at the value 0, 0 is equal to 2.2. So when you plug in 0, actually wait, I did that wrong. That's not equal to 2.2. It's actually equal to 4.2. So you can plug it in and you get this answer. And I think I made a mistake in my notes, actually, so I'll have to correct that in a moment. So, and we also get f sub f xy. It happens to be equal to f sub yx. And when you compute this, you end up getting this is equal to minus 4xy sine of x squared plus y squared. And so f of xy of 0, 0. Let me put this in green again. F of xy of I can't write. F sub xy of 0, 0 is equal to f sub yx of 0, 0 is equal to 0. And lastly, f sub yy is going to end up being equal to minus 4y squared sine of x squared plus y squared plus 2 times 1.1 plus cosine of x squared plus y squared. When you plug in 0, 0, this is actually going to be equal to 4.2 again. Okay, because this thing here is equal to 1, so that's this entire thing is 2.1 times 2 is 4.2. Okay, so now we have all the partial derivatives, which I messed up here, so let me correct these. So these are 4.2 and 4.2. You can write the Hessian matrix at 0, 0 is equal to 4.2, 0, 0, 4.2. This is a diagonal matrix, and therefore all the eigenvalues are 4.2, 2 times, but it's still just 4.2, and so they're all positive, plus 0, 0 is a local minimum. Okay, that was a lot of material. I'm now going to have you all try it out. So we'll do it step by step. So the first question is, I'm giving you this other equation. If you want, you can plot it out to take a look at what it looks like. But the important thing is this is the equation. What is the only critical point of f? So I gave you an equation with only one critical point, and I'm asking you what that is. Let me reset the chat. Would a Hessian matrix ever have more than 2 eigenvalues? So if you have a 2-variable function, it will never have more. It will always have 2 eigenvalues counting multiplicity. Sometimes they will be repeated, and so this is one of the things we've sort of not talked about too much. You shouldn't think about eigenvalues by themselves. You should think about eigenpairs. So an eigenvalue and a vector. And so a 2x2 Hessian matrix will always have exactly 2 eigenvalue-eigenvector pairs, and the eigenvalues might be the same. So in that particular case, the 2 eigenvalues were the same value. But no, you'll never have more than 2 eigenvalues. But yeah, that's a very good question. So the number of eigenvalues of a square matrix of an m by n matrix is limited by, well, n. And sometimes you'll have fewer because you have repeated eigenvalues, or if the eigenvalues are complex or something like that, and you're only working the reals. Okay, so it looks like everyone has been people are answering D. So let's work this out together and just make sure that's true. So f sub x here, well, what's the partial derivative with respect to x of this? Well, you just set y equal to a constant, and then you take the derivative. So this is 2x plus y minus 3 is equal to 0. F sub y is equal to x plus 2y is equal to 0. And so when you have the system of equations, 2x plus y minus, let's say that's equal to 3, x plus 2y is equal to 0, you can use the augmented matrix and do a Gaussian elimination, or you can just solve it directly. So x is equal to minus 2y, and therefore minus 4y plus y is equal to 3, and therefore minus 3y is equal to 3. So y is equal to minus 1, and if you plug that in, x is then equal to 2. So yes, so this is 2, negative 1. So that is the only critical point, and everyone got that correct, it seems. So now let's move on to the next half of the problem. So in order to do the further test, I'm going to ask, is this a minimum, maximum, or saddle point? Now remember, the critical point was at 2 minus 1. So what do we do now? Well, now we use the second derivative test. So we look at the eigenvalues of the Hessian matrix again. So, well, you need to take these partial derivatives, put them in the matrix, and then look for the eigenvalues. And then they'll tell you whether or not this is a minimum, a maximum, or a saddle point. And we'll give everyone a moment to figure this out. Oh, let me go ahead and Oh, okay, yeah, no, that's fine. Yep. So let's just go ahead and get a little started on it a little bit, since we are running a little bit low on time. But the basic idea is we need f sub xx, we need f sub xy, and we also need f sub yx, but in most functions that we deal with, that's going to be equal, and we need f sub yy. So hopefully you guys can compute all these values. And then, of course, then you need to solve for x sub xx 2 minus 1. What's that equal to? F sub xy 2 minus 1. What's that equal to? F sub yy 2 minus 1. Oh, okay, it looks like we've started getting answers. So once you solve for that, then you plug in all these values into the Hessian matrix at 2 minus 1. So what are these values equal to? Well, when you do take the partial derivatives, what you'll find is that this is just 2. Why isn't it writing out? This is a constant function, 2. This is 1, 1, and that's 2. So again, you're evaluating it at any point is going to be a constant. So you end up with a matrix that is 2, 1, 1, 2. And now we want to find the eigenvalues of this matrix. So that's just going to be 2 minus lambda, 1, 1, 2 minus lambda. That's equal to 4 minus 4 lambda plus lambda squared minus 1 is equal to 0. Lambda squared minus 4 lambda plus 3 is equal to 0. We've solved this one before. Lambda minus 1 times lambda minus 3 is equal to 0. Lambda is equal to 1 and 3. And therefore, this is... Oh, did I never give you the options? It seems like you guys all saw the options from your notes already, but yes. Did I just accidentally get rid of that? Oh, anyway. So therefore, this is a minimum. And so everyone was correct there. Okay, so this is sort of the intuition behind it. And what you need to do is you just need to solve for these eigenvalues. And then if they're both positive, then you know it's a minimum. If they're both negative, then you know it's a maximum. If one's positive and one's negative, then it's a saddle point. If you have a 0 eigenvalue, then you don't know. So it turns out if you have a 0 eigenvalue, then it's basically the same as the case where the second derivative is equal to 0. And you don't actually know whether it's a minimum, maximum, or a saddle point. Okay, so in my last couple minutes, I will give you a shortcut strategy. So that what I told you a moment ago is the reasoning behind everything. Oh, actually, let me show you the function first. So this is the function, and so as you can see, there is actually a local minimum there. Though it's not at 0, 0, it's at this other point here, down here. So at 2 minus 1. Okay, so let's go back. So there are some shortcuts you can take, and I'm not going to prove that the shortcut works, because unfortunately that involves a lot more linear algebra, though the proof is really quite nice. So if we have a function, two-variable function, we can find the critical points, of course, by setting f sub x and equal to 0 and f sub y equal to 0 simultaneously. So you solve for that, and then you have a critical point. So then I'm going to define this thing. D is equal to f sub xx times f sub yy minus f sub xy times f sub yx. So note, of course, that this is actually just the determinant of the Hessian matrix. Oh, that didn't work. This is the determinant at the Hessian matrix, which is why we call this D. So remember, the Hessian matrix was f sub xx, f sub xy, f sub yx, f sub yy. So this is just the determinant there. And it turns out that once you have this, then the quicker test is you just take the determinant, and there's a maximum if d is greater than 0, and the very first entry f sub xx is less than 0. There's a minimum if d is greater than 0, and f sub xx ab is greater than 0. And there's a saddle point if d is less than 0. And if d is equal to 0, we don't have enough information. I am not going to expect you to know why this works yet, but I'll give you a little... so basically this works because of a couple really important facts in linear algebra, which we haven't really discussed. So it turns out there's a very deep relationship between the determinant and the eigenvalues. So it turns out that the determinant is equal to the product of all your eigenvalues counting repeats. And this is just generally true. This is also why if one of your eigenvalues is equal to 0, which means that you set some... which means that you collapse some vector equal to 0 when you apply the matrix, then the determinant's also equal to 0 because the area is equal to 0 since you're collapsing everything into a line. And the other important fact is the sum of the diagonal elements, the trace, is equal to the sum of the eigenvalues counting repeats. Now, I'm not going to prove this in this class. This is a very important fact about linear algebra, which we might use later as well. But basically, by using these two facts together, you can prove that if the determinant is greater than 0 and the very first and the top diagonal term is less than 0, then both of the eigenvalues have to be positive. And if the determinant is greater than 0 and the top term is greater than 0, then both of the eigenvalues have to be, negative in the case of the maximum and positive in the case of the minimum. And of course, if the determinant is less than 0, since you only have two eigenvalues, and therefore to be less than 0, one has to be positive and the other has to be negative. So let's quickly apply this to the previous example, just as we finish up the class. So the example from above, we had a Hessian matrix that was equal to 2, 1, 1, 2. Well, the determinant, 2, 1, 1, 2, is equal to 4 minus 1, which is equal to 3. And the top term, f sub xx, is equal to 2. And therefore, we have a local minimum. So using this determinant test is often significantly faster than actually computing the eigenvalues. You'll get the same answer. It is faster, but because it is you may have to memorize that rule. So you can always use the eigenvalue test, but the determinant test is sometimes a little bit less computation. And with that, I think that is the end of class. So thank you all very much, and I will, of course, stick around for office hours in case you guys have any additional questions. I think I'm going to stop the recording here.